Okay, ever stop to think about, the stuff between the stars? Not just the stars themselves, but all the invisible chemistry happening out there. Well, today we're diving into something really fascinating. A new study that's kind of mapping how a key element, sulfur, actually changes form way out in space.
Uh-huh. It's giving us this, like, hidden view of the Milky Way's chemistry, some really fundamental secrets.
So let's get into it. This deep dive is all built around a really significant X-ray study. It involved a big international team using data from the XRISM spacecraft, that's Japanese-led, right?
That's right, XRISM-A stands for X-ray Imaging and Spectroscopy Mission. And our goal here really is to break down these observations for you.
Yeah, what did they actually find about sulfur out there?
Exactly. We want to show you what they learned and, crucially, why it's actually a pretty big deal for understanding, well, our whole cosmic neighborhood.
All right, let's jump right to maybe the most exciting part, the big reveal. For the first time ever, scientists have directly seen elemental sulfur out there in space as both a gas and a solid.
Yeah, both forms at once,
Yeah.
which is pretty groundbreaking for understanding how elements cycle through space.
How did they even manage that? Seeing both states.
It comes down to the technology on XRISM, specifically X-ray spectroscopy. This lets you analyze the energy from X-rays really, really precisely, like getting a fingerprint for the elements.
Okay.
Oh, and just for context, it's pronounced XRISM.
XRISM, got it. And sulfur. It sounds maybe a bit obscure, but it's actually incredibly important, isn't it?
Absolutely. It's vital right here on Earth for how our cells work.
So finding it out there, seeing how it behaves, it connects back to us, to the ingredients needed for life.
Exactly. Leah Corrales, she's an astronomy professor at Michigan and the lead author on this paper. She pointed out that sulfur shifts between gas and solid pretty easily. But seeing both, that needed XRISM's unique capability.
Okay, so that leads into this mystery scientists have been wrestling with, right? The vanishing sulfur problem.
Uh-huh.
They knew sulfur was out there as a gas. They could see it with ultraviolet light in, the general space between stars.
Correct. But the puzzle was, when you looked at the denser areas, think of molecular clouds, these huge nurseries where stars and planets are actually forming.
Yeah.
The gaseous sulfur just seemed to disappear, vanish from view, using those UV methods.
So everyone kind of assumed that it must be turning into a solid.
That was the leading theory, yeah,
Ah.
that it condensed maybe onto icy dust grains or combined with other elements into solids.
But they couldn't directly see the solid stuff before?
Not easily, no. It was more an inference. We knew it had to go somewhere. Solidifying made sense chemically in those cold, dense places, but direct proof was missing.
Which raises the obvious question. How do you find something that's basically hiding from you?
Good question. And that's where this team's method comes in. It's really quite clever.
You mentioned it's like a medical X-ray.
Kinda, yeah. Think about it. For a doctor's X-ray, you need the source emitting the X-rays, the patient, the thing being studied, and the detector behind them.
Right.
So Corrales and the team did something similar, cosmically speaking. First, they picked a target region in the interstellar medium. Not too thin, not too thick, just right, density-wise.
Okay.
Then, they needed a bright X-ray source behind that region, a cosmic backlight.
And they found one.
They did. A binary star system called GX340 plus 0. It's pumping out a lot of X-rays.
Wow. Where's that?
It's way over on the other side of the galaxy from us, actually.
Yeah.
Over 35,000 light years away, down in the constellation Scorpius.
Okay, so they have their interstellar patient and their X-ray source. Then what? This is where XRISM comes in.
Exactly. They used XRISM's Resolve instrument. It's incredibly sensitive to tiny differences in X-ray energy. By measuring the X-rays from GX340 plus 0 after they passed through that interstellar cloud, they could see which energies were absorbed or altered. And those alterations, they matched the signature of sulfur, not just as a gas.
But as a solid, too.
Yes. And even more specifically, they found signs it was likely combined with iron.
Iron. Okay, that's interesting. So not just solid sulfur, but specific compounds.
Well, they started modeling what kind of iron-sulfur compounds would produce the exact X-ray signature they saw. Elisa Costantini, one of the co-authors, mentioned that interstellar chemistry is, pretty weird compared to Earth.
I bet.
But their models for sulfur mixed with iron were a really good match for what XRISM detected.
Does that fit with anything else we know? Iron and sulfur together in space?
It does, actually. We find iron-sulfur compounds like sulfides quite commonly in meteorites that fall to Earth.
Ah, so maybe those form in these clouds and then travel.
That's been the thinking, yeah. This provides strong evidence for that pathway. The sulfur solidifies, maybe gets locked into dust or rocks, and can then move around the galaxy.
So did they narrow it down? What specific compounds are we talking about?
They proposed a few candidates that fit the data really well. Things like pyrite, troilite, and even pyrite, which, is sometimes called fool's gold.
Wait, seriously, fool's gold floating in space.
Potentially, yeah.
Yeah.
Based on the X-ray signature, pyrite is a good candidate for some of the solid sulfur they detected.
That's amazing. Did they, double check this somehow?
They did. They also looked at data from another X-ray binary, 4U163-472, shining through a different part of space. And the sulfur signatures there helped confirm their findings about the iron-sulfur connection.
So, pulling this all together, what's the big takeaway? Why does tracking down sulfur in both forms matter so much?
Well, it's about the sheer level of detail XRISM gives us. Brian Williams, he's the XRISM project scientist at NASA Goddard. He pointed out that NASA's Chandra X-ray Observatory looked at sulfur before, but these XRISM measurements are way more detailed. The most detailed yet, he said.
More detail means a clearer picture of the chemistry.
Exactly. It's not just about sulfur in isolation. It helps us understand how all the heavier elements, the ones forged in stars, get distributed and recycled throughout the galaxy.
Right.
How they move from gas to solid, maybe into new stars and planets. It's fundamental to cosmic evolution.
And the fact that the X-ray source they used, GX340 plus 0, is so far away, that gives them a really long line of sight through the galaxy, doesn't it?
Precisely. It's a unique probe, as the researchers put it, across a huge swath of the Milky Way, not just our local backyard.
So we're getting a broader view of how this element behaves everywhere.
Which just goes to show there's still so much we're figuring out about our own galaxy. These new tools are opening up whole new perspectives.
And XRISM itself, it's a big international effort, right?
Absolutely. Led by JAXA, the Japanese Space Agency,
Okay.
but with NASA heavily involved, and contributions from ESA, the European Space Agency, too.
And that resolve instrument, the key piece here, was a joint NASA-JAXA development.
Yeah, a great example of different agencies working together to push the science forward.
Wow. So we went from sulfur in our bodies all the way across the galaxy, seeing it hide and reappear thanks to X-rays.
It's quite a story, isn't it? This study really gives us a fantastic new window into those essential chemical cycles happening out there, seeing how these vital elements get spread around, locked up in solids, maybe released again. It's how galaxies build things, including planets like ours.
It really makes you wonder, doesn't it? If an element we think we know, like sulfur, has these hidden transformations out in space, what other chemical secrets is the Milky Way holding on to? What else is waiting out there for the next generation of these amazing instruments to uncover?